We are talking about relative extrema. I have the function f of x is equal to x cubed minus 2x squared minus 15x minus 2, and we're going to go ahead and look at the graph first before we actually start finding that relative extrema. So the dots right here, the red dots that you can see on the graph, this is the places where I'm indicating relative extrema. For example, this particular red dot here is going to be our relative maximum, and this dot here will be our relative minimum. Now, as we can see, the graph is increasing up to whatever this number here is, and then decreasing, and then it is increasing. All right, well, let's look at the math. So the first thing we're going to do is we're going to take the derivative of this function up here. So the derivative, f prime of x, is equal to 3x squared minus 4x minus 15. We're going to take the derivative, set it equal to 0, and then solve for x. And what I do here is I go ahead and factor this into x minus 3 times 3x plus 5, and hopefully you can remember how to factor. Right, so x times 3x is 3x squared, x times that's 5 is 5x, and then minus 9x, and 5x minus 9x gives us negative 4x, and then negative 3 times 5 is negative 15. Well, then what I do is go ahead and take each one of these factors, set them equal to 0, and then solve for x. So this first one here, x minus 3, set it equal to 0, there x is equal to 3. Then I take this second factor here, set it equal to 0, solve for x, and we get x equal to negative 5/3. Well, these two numbers that we just found, those are our critical numbers. Now I go ahead and draw this graph listing my critical numbers as negative 5/3 and 3, and then we choose some test points like negative 2, 0, and 4. Remember, we want to choose some nice points. So when we plug those into the derivative, they're easy to calculate. So taking negative 2, plugging it into the derivative, I get a positive number out, 5. And that tells us that the function is increasing up to negative 5/3. We plug 0 in to the derivative, right, that's our second test point. We get a negative number in, so we know that the function is decreasing. Therefore, we know that there's going to be a relative maximum at negative 5/3. Then we go ahead, plug in our last test point, plug 4 into the derivative, and we get a positive 17 out. And I'm not sure why there's a parentheses here. Let me get rid of that. Okay, I think that parentheses somehow I had to put it back in. We're going to go ahead and plug our critical number in, which is negative 5/3, into the function. We get 346 over 27. So that's going to be, we now have the actual point where our relative extrema is going to occur, and then we go ahead and plug 3 in, and we end up getting negative 38, which I need to scroll down the screen. Okay, a little better. We get negative 38 out. So now we have our relative max and our relative minimum. So I'm now indicating that right here, abbreviating maximum for just max. So the max, that actual red dot on the graph we were looking at earlier, is occurring at negative 5 over 3, 346 over 27. And our minimum is occurring at 3, negative 38. So we could say that this function is increasing from negative infinity up to negative 5/3, and also increasing from 3 to infinity. Now I separate these two intervals here by a comma, and you may see this as with a comma, or you may see a union symbol here, unioning two sets, but I'm just going to use a comma here. Okay, and we know that this function is decreasing from negative 5/3 comma to 3. From negative 5/3 to 3. Now let me say something here real quick. Sometimes we get confused about this, but this is an actual point on the graph. Okay, this is an interval, right? An interval. Point on the graph, an interval. I know both these notations look similar with these parentheses, but this is an interval of numbers. Point on the graph. Okay.